Oh, yeah, thank you very much.
All right, welcome back to our weekly seminar. This week we have a talk from Professor Masahiro Yamamoto. He received his PhD from the University of Tokyo in March 1988. He has been a professor at the Graduate School of Mathematical Sciences of the University of Tokyo since April 2010, where he was previously a research associate from April 1985 to March 1990 and an associate professor from April 1990 to March 2010. Since 2024, he has also been a professor at Zonguldak Bülent Ecevit University in Turkey. His research topics include inverse problems for partial differential equations, fractional partial differential equations, and industrial mathematics. He has published almost 400 peer-reviewed papers and received almost 8,000 citations from more than 3,000 publications. This is according to the Mathematical Reviews database of the American Mathematical Society. Today, he will give us a presentation about uniqueness and stability results for inverse problems for time-fractional diffusion-wave equations. Please, you may start.
Thank you very much. Yeah, still, I'm very sorry. Your voice is a bit unclear. Yeah, propagated. But anyway, if everybody can hear me, then I would like to start. I hope my voice can
Yes,
well
yes, your voice is
propagate.
clear. Yes, your voice is clear.
Okay, okay. Thank you very much. And first of all, I would like to thank all the organizers for this seminar series, and especially happy thanks to Dr. Fernandez. And thank you very much. And that is a very nice opportunity for me to make a presentation about my recent works on time fractional so-called diffusion wave equations. Okay. Then, at first, please let me start the motivations. Okay, the following is a very naive explanation. And let us imagine that we will consider propagation or diffusion of some harmful, like contaminants, sometimes very dangerous radioactive isotope. But the media is the soil, and the soil is highly heterogeneous media. Then very important to predict of the diffusion phenomenon. But however, thanks to the heterogeneous media, the diffusion profile indicates quite peculiar, anomalous pattern. And very roughly speaking, if we will use a classical advection diffusion equation, very so-called very fast decay, say very fast propagation or decay, and according to the time, rather quickly, namely exponential decay. However, quite frequently in the field, one can observe not so quick, rapid decay, and quite frequently contaminants remain longer near the contaminant source. Therefore, from the practical viewpoint, it is very important how which equation can be a better model equation for such anomalous diffusion in heterogeneous media. Then here we will consider mainly time fractional. We will not consider space fractional. Mainly we will consider time fractional diffusion equation. That is the motivation. Anyway, this is very naive figures. Okay, then now let us start slowly about mathematics. Then we will consider so-called Caputo derivative or derivation Caputo derivative. That is a definition. Sorry, I have changed the notation, the dt alpha. Then we will, for the moment, consider alpha between 0 and 1. Then this is the classical definition of the so-called Caputo derivative. Okay, then very simply writing, our main target is time fractional diffusion equation. If alpha is between 1 and 2, frequently used, called time fractional wave equation. But anyway, we will consider time fractional diffusion equation like that. Then just for simplicity, we will consider Laplacian. Then here is not the first order term, of course, this is the Caputo derivative. Then we will attach suitable boundary condition and initial condition. Oh, sorry, this should be U, sorry. Then can model some anomalous diffusion. I think this is quite classical with Riemann-Liouville derivative. Therefore, maybe I need not explain the motivation of this form. But anyway, this corresponds to alpha times derivative. Then, according to like a practical motivation, we will consider the forward or the direct problem for time fractional diffusion equation. Of course, we must be concerned with the boundary condition, and we must be concerned initial condition. Then, natural, very naive question that unique existence of the solution. If exists, what is the regularity and so on? That is very fundamental questions. Okay, then just for your reference, time fractional diffusion equation is, in one sense, completely different from any classical diffusion procedure, including diffusion process on the fractal. Namely, if one will discuss the fundamental solution, principal term of asymptotic behavior of the fundamental solution always keeps some singularity in the space X. Indeed, in the paper by Eidelman and Kochbe 2004, actually they consider more general case, but just for our reference, very simple time fractional diffusion equation. Then G is a fundamental solution. This describes the diffusion at t equals 0, where Dirac delta concentrating density is given. Then that part is, except for the difference of the index or the power, in principle same. But new aspect, new factor is like that, x minus y minus power. Of course, if alpha equal 1, no singularity. But alpha is between 0 and 1, this is definitely a singularity. Then also, there are many works for diffusion process on the fractal. Also, that case, structure of the fundamental solution, roughly speaking, has no singularity in X. Therefore, one can say that completely different for our time fractional diffusion is completely different from others. Of course, this special singularity describes remaining effect of contaminants near the source term. Okay, this is one character. Okay. Okay, then let us return to the initial value boundary value problem. There is some delicate issue. Namely, I think more or less quite well known, namely time fractional equation, one must be careful of the initial condition. If we consider some non-smooth, non-homogeneous term, that is very simple example. Just we consider ordinary form. Then 1/8 is the order. Then this is minus quarter. Then of course this is L2 function, square integrable. Then we will attach boundary condition. However, in this case, no solution. No solution to initial value problem, because one natural candidate is 1/8 times derivative is consequence minus quarter. Therefore, to non-homogeneous term. And for example, if we assume that f is L infinity in time t, always we can prove that U is continuous. Therefore, no such delicacy. Therefore, for the moment, simple strategy, whenever we will consider inverse problem, let us assume that non-homogeneous term, we assume non-homogeneous term has L infinity in time t. Okay. Then, now, this is like a grand plan. From my viewpoint, still many issues related to time fractional partial differential equations are not comprehensively solved, say, studied. Then, therefore, also on the other hand, many practical requests for mathematical analysis or mathematical backgrounds. This is very primitively saying that this is our very strong incentives. Then our mission is, in principle, I am a mathematical analyst, not very few numerical researches. Then the one kind of mission is that we should consider theoretically that result should support real-world applications and vice versa. Our theory should be supported also by real-world applications. Then still, in spite of the practical importance, not comprehensive theories for time-fractional diffusion equation. Sorry, I can say so. I can dare say so. And not very complete studies compared with the classical theories of partial differential equations. Therefore, for the moment, let us consider, in a sense, piece by piece. Then today, mainly, I will focus inverse problems. Then, more or less, I picked up materials from the published or preprints in archive. Therefore, I will not touch the detail of the proofs. Of course, if you are in any sense interested, maybe later or somewhere I should post the references because submitted references are not so complete. But anyway, I would like to try to convey some keys of the proofs as well as, of course, the statement of the inverse problem. Okay, then. Okay, but then here is this is just simple explanation. We have a quite wide region of research field of time-fractional differential equation and many problems. And just at random, and the so-called direct problem or further problems, many things. And fractional calculus is very traditional since Leibniz, then quite well established. But how to use that classical fractional calculus effectively? Also, operators theoretic approach is possible, and asymptotics, well-posedness and comparison principle, and also degenerate parabolic equation related with a global climate, and also more or less nonlinear theory, including blow-ups, stability, instability. Also many kinds of inverse problems, and also control problems, optimal control. That's why many issues are waiting our working. But here, just I will pick up several topics mainly from the field of inverse problems. Okay. Then now inverse problems. Then just for warming up, like a preliminary consideration. Mainly, today's talk assumes elliptic part is symmetric. In some cases, we can delete symmetry, but more technical. Therefore, please let me assume that elliptic part, for example, this minus a is symmetric elliptic operator. Of course, for simplicity, you can consider minus a is just a simplest case, Laplacian. Then we will consider always bounded smooth domain. Then boundary condition, for example, zero Dirichlet or zero Neumann boundary condition. Then it is well known that we have eigenvalues for A. Then also simplicity, we assume here is a minus A is non-positive. Therefore, all the eigenvalues are positive. Then just notational convenience, we are numbering all the eigenvalues according to the multiplicities. Therefore, this is not a set sequence. Some value of, say, lambda 3 may repeatedly appear according to the multiplicity. Then phi n is the correspondent eigen functions, linearly independent and normalized. L2 norm is 1. Then it is well known that phi n forms an orthonormal basis in L2 omega. That is a very basic notational preparation. Then consider initial value boundary value problem. Then after that, one can apply at least formally very classical result, the method of Fourier or separation of variable method. Then we can write down the solution U to this direct initial value boundary value problem. This is also quite well known. Then parentheses always for saving the spacing, parentheses mean that L2 scalar product. Okay, then this is the scalar product of A with respect to phi n. E alpha 1 is a classical so-called Mehta function defined by the power series. This is the entire function in Z. Then we can prove under this situation, we can prove some regularity, but maybe for the moment, this is not very important. Okay, now this so-called solution representation is a fundamental tool for our consideration on inverse problems. Okay, of course, if alpha equal 1 corresponds to the classical diffusion equation, alpha equal 1, just for your understanding, if alpha equal 1, E11 is nothing but exponential function. Therefore, this solution formula includes very classical Fourier solution to the heat or classical diffusion equation. Okay, then also as a glossary or as a toolbox, I will present very important properties of the Mehta functions, which are all very, very classical. First property is alpha 1, and for the moment, we assume alpha is between 0 and 1. Then this absolute value is estimated by this order. Minus S, negative, this is bounded. Then S is always positive, but E alpha 1 minus S, we have asymptotic expansion. Principal term is like that, plus 1 over S squared. Then third property is very characteristic and important by the complete monotonicity. And complete monotonicity asserts much more, but we will use mainly positivity of E alpha 1 minus S is positive for all non-negative S. This is surely correct for alpha between 0 and 1, but in general not for alpha greater than 2, greater than 1, sorry. Okay, then just a small exercise. If alpha equal 1, of course, that formula is correct, but alpha equal 1, then this is infinity, therefore no term. Then next term also 0, 0, 0, 0. Then actually all the finite number of terms must be 0 if alpha equal 1. Therefore, simply we can get no clear principal part. Namely, this is perfectly correct. Minus exponential is higher rapidly decay than any polynomial order. Therefore, second asymptotics can make sense, not alpha equal 1. Okay. Then that is just a minimum preparation for the next preliminary sorry, consideration. Okay, then at first, just very simple, this is like an exercise level, but let us calculate H2 norm of the solution at time t. Then simply we can apply Parseval's inequality, and H2 norm is equivalent lambda n multiplied Fourier coefficient. Therefore, This is like a norm equivalence. H2 norm squared is like that. Okay, then let us substitute the first property, important property of the Mittag-Leffler function. Then here is 1 over, sorry, like that. But here, lambda n T alpha. Therefore, the order itself, lambda n T alpha. Therefore, here and here, lambda n squared is cancelled, remaining just T minus 2 alpha. Then, of course, this is nothing but L2 norm of A. Therefore, very directly, we can prove this kind of estimate. This implies, of course, if initial value is in L2, UT is H2. Then decay rate is at least T minus alpha. This is a consequence, very simple consideration. Then now, natural question. L2 initial value, then H2. Then this is smoothing, L2 to H2. 2. Then next natural question, that is the best possible smoothing effect. Never H3, never H4. Then also this decay, T minus alpha, is this the best possible decay rate? Anyway, at first I will prepare very easy material. And the answer, both answer is that yes, both are best possible. Then the next, in principle, all the sections are quite short, and I believe quite simple to you. And about the decay rate, one can state, for example, small omega is arbitrarily chosen subdomain. Then L2 initial value. Then we assume in small such chosen subdomain omega, L2 norm is faster decay than T minus alpha. Then we can conclude initial value originally vanished in small omega. That is one result. Of course, this kind of property is absolutely impossible for alpha equal 1, the heat or classical diffusion equation. In other words, alpha between 0 and 1, U dot T, positive time, still keeps quite rich information of initial value. This is a different aspect from the classical diffusion. This is maybe one reason why this is anomalous diffusion. Then some other results and related results can be proved. In some cases, we can prove necessary and sufficient condition that initial value is vanishing in the measurement subdomain or measurement point x0. But maybe the proof is more complicated, but similar to very basic result. Then the proof of Theorem 2.1 actually very simple. Then, as I mentioned, that our main ingredient eigenfunction expansion of the solution. This is the first. And the second ingredients are important properties of Mittag-Leffler functions. So far, I represented upper estimate and asymptotic expansion and positivity. 3 I presented. But now we will use eigenfunction expansion and asymptotic expansion. Then we will substitute asymptotics of Mittag-Leffler function into representation formula of the solution. Then rather directly we can get this kind of asymptotic expansion, namely principal part coming from T minus alpha. Then other part is order T minus 2 alpha. Then one thing that this is not so essential, but a scalar product with phi n divided by lambda n phi n. Then this is like a very simple spectral representation. This is nothing but A inverse initial value A. Then this is a short representation. And also this term is nothing but the order T minus 2 alpha. Then let us estimate L2 small omega norm. Then simply principal part of that norm is coming from this, like that. Then other part is residue term, namely T minus 2 alpha. But by the assumption, this order, we assume that this order is faster than T minus alpha. Therefore, this must be 0. This coefficient must be 0. In other words, A inverse A must be vanished 0 in small omega. Then after that, we can operate elliptic operator to both sides. Then we can obtain A is 0 in small omega. As a proof, that's all. Therefore, such a characteristic property comes from the property of Mehta functions with alpha not 1. This is the point. Then next is backward well-posedness. This is concerned with smoothing effect. As I said that if initial value is L2, any positive time, regularity is H2. Then plus 2 by the Sobolev index, plus 2 smoothing. Then next theorem is also backward well-posedness, and simultaneously this indicates smoothing properties, smoothing index by the Sobolev space is exactly 2. Okay, then the statement is as follows. B picked up from H2, H10. Then we will consider backward problem, namely you satisfied this, but we don't know initial value, but at capital T, we are given. Then our task is that we will find U in 0 and capital T. Answer is there exists a unique solution. Of course, H2, H10 must be assumed for final value. Then there exists a unique solution and also norm equivalence. Then, of course, and also the proof is very simple and also quite old result, but the proof is based on solution formula or representation eigenfunction expansion of the solution. Next page, I will show, but the proof is sufficiently simple. Of course, other thing is that what will happen non-symmetric A. Then we have proved with Professor Floridia and DZ1 about 5 years ago, and also the same result. And rather different aspect for backward well-posedness is the case alpha between 1 and 2. And I will skip the statement, but there are infinitely many exceptional points or exceptional values of capital T for well-posedness. But anyway, I will skip. Then, for your understanding, please let me talk about the proof. But the proof is quite simple. The same, asymptotic expansion and eigenfunction, also positivity. Then at first, asymptotics of Mehta function can give rather directly for large N, all large N. This is lower bounded, some constant, positive constant over lambda N for all large index N. On the other hand, positivity means that each N never 0. Therefore, this and this we can combine for large N. This uniform lower estimate can take care, but not large N. Anyway, finite number we can consider. Those are non-zero, positive. Therefore, if we change C1 sufficiently small, for all N, we can get this lower estimate. Then after that, we will plug this inequality into eigenfunction expansions. Namely, B is the value at capital T. Therefore, like that. But that factor is more or less estimated from the below 1 over lambda n. Therefore, we can get each Fourier coefficient. A, this is a Fourier coefficient, is equivalent or upper and lower estimated with factor lambda n. Then we can return to the possible inequality. We can get A squared L2 norm is equivalent lambda n squared Fourier coefficient. This is equivalent to H2 norm. That is a proof. Of course, as I said that for symmetric case, everything can be done by eigenfunction expansion explicitly. Therefore, non-symmetric case, more works are necessary, but already done. Then, okay, that is. Now, please let me move to the next type of inverse problem, namely inverse source problem. This is one example. This is a catastrophe happened in Japan 2011 in March, namely explosion of Fukushima #1 plant of Unit 3. Namely after the great earthquake and the tsunami, nuclear power plant was damaged. Then electricity was lost. Then interior pressure became higher. Then explosion and a lot of cesium emission. This is a very serious incident. Okay, here is power plant, nuclear power plant. But please understand that this is more or less source term. Then taking into consideration anomalous diffusion in the air or in the soil, time fractional diffusion equation is one adequate model equation. Then with source term, but that source term is explosive, namely source term was activated quite short period, not 1 day, not 1 week, just maybe at most 30 minutes. Then that case, which is our model equation. That is the same time fractional diffusion equation, but we will model source term by the separation of variables, namely t dependency and the spatial distribution of the source term. Then typical inverse source problem is that by extra data, we want to determine mu t or f of x, or both. Okay, then as I said that for avoiding delicacy of the initial value, we will assume that L infinity in time t of the source term. Okay, then rough expectation is that returning to the decay and the initial value, some information of the solution can be preserved well, better than heat equation. Therefore, for the determination, say inverse source problem also, same data or some data can determine much more compared with the heat equation. This is a very rough, say, expectation. But a very classical formulation of the inverse source problem is like that. We assume initial value is 0. Then we will take arbitrarily choose subdomain. Then that is the uniqueness, namely omega times 0t is 0, then nothing. Then proof is very easy, therefore I will skip. But actually, under some condition of mu, the same data can guarantee the uniqueness simultaneously both initial value A and the spatial distribution F. That is a completely different uniqueness from the classical diffusion equation. Then the main statement is as follows. This is the same, our main system, but this is not necessarily 0. A is also unknown. F is unknown, but we assume that mu is given. We assume like that. Mu is of course not identically 0, And after some time, capital T, quiet, no source term. Mu T is 0, always after time T. Then there is so far no counterexample, but we must assume that order is some, for order, some exceptional set, countably infinite sets of alpha, then alpha is not belonging to this. We can prove that after the incident, say capital T incident perfectly stopped. After that, nothing. After stopping incident, we will choose 2 moments, then observe taking the data T1, T2. Then this is 0, we assume. This is like a uniqueness. Imply that both initial value and spatial distribution of the source term, both are 0 everywhere. And this means that our data of time fractional diffusion equation can keep preserve information from initial value A, the information from spatial distribution of the source term. And the proof is quite technical, but the key is still same. Namely, main technique is that eigenfunction expansion and asymptotics of Mehta-Leffler functions. Then for getting 2 independent relations for determining Fourier coefficients A and F, our proof needs this kind of condition. Therefore, this is, I don't know, technical or essential. But anyway, this means that in a sense, like a resonance order of the differentiation can preventing from the uniqueness. But anyway, infinitely, of course, discrete exceptional set, but the countably infinite. Okay. Then next type is determination of the kernel function. And then let us start to consider different type of the equation. But here is so-called relaxation coefficient. We will introduce, and also the physicists has been considering this kind of generalized fractional derivative. And of course, if gamma equal 1, this is nothing but a classical Caputo derivative. Then here for just one possible formulation, we will put source term artificially. Then a condition for lambda is necessary. And here we assume some regularity, and gamma is analytic. And positive, also this is quite natural. And this is a bit, looks special, but this is non-positive. And in particular, if gamma prime is non-positive, always this condition is correct. But more general, we need this kind of condition. Okay. Then if we have this condition assumed, also not very trivial, but we can prove that order preserving, namely input, in this case, distribution input is non-negative. Automatically, U is also non-negative. Then there are several works for that. In the class of gamma, say with some Stiltes class, like by Kochubey and the Zahia and the others. But our class is rather different, like that. Then within this class, well-portness has been proved by my Turkish colleague, Gergerian, and Sarikoze by Ram and myself. But here we consider inverse problem, namely given chi, this is a boundary input, and we choose interior point. Then this interior point, we want to determine index alpha and gamma. Okay. Then namely for the uniqueness, we must prepare 2 equations, 2 relaxation coefficient, gamma and gamma 1. Then, but the same interior input. Then also for gamma 1, we assume the same condition. Then main result here is the uniqueness, namely, with this, if this is 0, nothing. Therefore, we must add some input interior. This means that chi is non-negative, but not identically 0. Of course, this is admitting that support of chi is very small, like a Dirac delta, but does not change the signs we are given. Then after that, we start to observe at monitoring point x0. This case, starting from 0. Then if two data are same, we can conclude that our unknown relaxation or kernel function can be same. This is the uniqueness. Then the main part of the proof for this uniqueness also indicates somehow typical argument for the uniqueness related to time-fractional diffusion equation. Therefore, I would like to show the sketch of the proof, but not so complicated. Okay, then, sorry, just a minute. Something wrong. Okay. Then that is part of the kernel function. Okay. Then also Qt is like a difference between two kernel functions. Then we will take the difference between two equations in U and in U1. Then the difference is denoted by Y, and capital R, this is not so important, but U1. Then we will consider just for simplicity minus Laplacian with 0 boundary condition. Then first step is that this is not very trivial, but one can prove iteration or fixed point theorem, namely gamma is analytic for positive t. Then we can prove that U itself is analytic in positive t. The same gamma 1 is analytic. Then by contraction argument, we can prove that U1 is analytic in positive t. This means that analytic minus analytic functions. Therefore, Y itself analytic for all t positive. But by our assumption, from 0 to capital T, two data are same. In other words, Y x0t is 0 if t is in 0 to capital T. Then thanks to the analyticity, this means that Y x0t is 0 for all positive t. This is somehow typical step for proving the uniqueness. By means of analyticity, we can extend the data coincidence up to infinity, t equal infinity. Then next step is more or less common. That's why we want to naturally to take the Laplace transform. Of course, some possibility taking a Laplace transform must be proved, but I will skip. I will show only the essence. Then let us take the Laplace transform of Yx0t with respect to t. Hat means Laplace transform. Then we applied a quite classical formula of Laplace transform of fractional derivatives. Then like that. Also, of course, here is we must take care of Laplace transform, but that is convolution type. Therefore, Laplace transform of this part is a product of the Laplace transforms of two factors. Therefore, as a conclusion, taking the Laplace transform and taking the inverse of like a resolvent, lambda h hat lambda. If minus lambda h hat lambda is the resolvent of A, then we can take the inverse Then after substitution x0, then by this condition, this must be 0. Therefore, we can conclude that, of course, lambda factor does not matter. Then q hat lambda blah blah blah, blah must be 0 at x0 if lambda satisfies. Then after that, I will skip the details, but we will apply strong maximum principle. Because here is positive, because H is positive, because we assume that lambda is positive. Therefore, after taking Laplace transform, H hat is positive. Therefore, this is positive. Therefore, zeroth order term of elliptic equation is positive. Then, of course, this function satisfies zero Dirichlet condition. Therefore, we can apply strong maximum principle. Then the checking other things, of course, this function cannot be a constant function. Therefore, we can conclude that second factor is not zero, actually positive. Okay, except for some exceptional points accumulating at the infinity. But this does not matter because except for the discrete set of lambda, this is not zero. Therefore, except for discrete set, q hat lambda is 0. Like that. It's some outside of some discrete set of the positive real number, q hat lambda equals 0. Then q hat is analytic as a Laplace image. Therefore, Laplace inversion means that q itself must be 0. But the q itself, and this is just a difference between two solutions, two kernel functions. Yeah, that is scenario. Now I bits must be hurry up, and also important inverse problem is that inverse coefficient problem. I have not yet discussed such typical type of inverse problems, namely determining of coefficient, mainly spatially dependent coefficient. Unfortunately, for this case, we have no comprehensive method. The main reason is that we have no convenient formula of integration by parts. Therefore, case by case, some limited situation. Then now this is joint work with Imanibirov this year, Imanibirov and Kazufumi Ito. Then we will consider only one-dimensional time-fractional diffusion equation, only one dimension. Then zeroth order term, here is P, here is Q. Then we will consider one-dimensional interval. Then we assume that same initial condition, some regularity. And at one endpoint is Neumann zero boundary condition. Then our result is as follows. A never vanishes up to the boundary. Then some regularity for solution and the coefficient. Then we assume that Dirichlet data are same at one endpoint. Then we can conclude that P is the same as Q on the whole interval. And this means that one thing is very clear. Let us consider classical unique continuation property. Unique continuation property means that equations are given perfectly. This means that Px is given. Then satisfies. Then unique continuation means that Neumann data are 0, one endpoint, and the same endpoint, Dirichlet data are 0. Then unique continuation means that U itself vanishes everywhere without any information of initial value. That is a unique continuation. But this case, our case is not unique continuation. The coefficient is unknown. Therefore, in a sense, naively thinking, only so-called Cauchy data are not at all sufficient. Some spatial extra data is necessary. Then here we assume initial value as a spatial data are given. Then this is given and the so-called Cauchy data are same. Then we can guarantee the uniqueness in determining the coefficient. And this kind of also one-dimensional case, but this kind of result has no correspondent result even for the parabolic equations. Parabolic equations, I have been working many years. For the parabolic case, we cannot take initial value, but any positive time, say t0 positive, the data are same, we can conclude. But by according to the technique like L2 weighted estimate, Kahneman estimate, in the parabolic case, we cannot in general take 0. But in one-dimensional case, we can take 0. Then proof is rather characteristic, very classical technique and transformation operator, mainly owing to Levitan. But I will skip that. But anyway, also, this transformation operator is very useful for studying one-dimensional eigenvalue problem, like a so-called Sturm-Liouville system. Anyway, but I will skip that. Then maybe I think 5 minutes. Yeah. Okay. Then other important investment is that determination of fractional orders, and because fractional order alpha indicates very important physical property of the media. Therefore, the determination of such alpha. Okay, then the notational preparation. U alpha, depending alpha, and also initial value AB. This is maybe not perfect notation, but the U alpha AB satisfy this. But if alpha is satisfied this, we don't consider B. But if alpha is greater than 1 for well-posedness of the direct problem, we must assume U x0 and first derivative in time t U x0, A and B. That's why let me write down the solution U alpha AB. Then this is the same symmetric, and the initial value A and or B are sufficiently smooth. The inverse problem is that interior point is fixed. Then one end point, monitoring point x0, and alongside the time interval, can we determine the order between 0 and 2? Okay, we assume that everything is given except for alpha. Then answer is a bit peculiar. We assume monitoring points, at the monitoring points, one of initial value is not 0. Then under this quite weak assumption, of course, in other words, we can change U. One of the two solutions are not identically 0, but anyway, AX0 not 0 and other things are not 0. Then this data can guarantee the same alpha equal beta. This is quite also different from other, say, alpha equal 1, because order alpha itself is independently, uniquely determined, although initial values are not necessarily same. Like that. But moreover, even some formulations, even alpha and beta can be uniquely determined, even if elliptic paths are unknown. Initial values are perfectly unknown. Then that is a second theorem. Like that, and even elliptic paths are not necessarily same. But Dirichlet data are both 0 and both are same. And also normal derivative is same, any small part of sub-boundary. Then we have only two possibilities, alpha equal beta, or originally both solutions are 0. Then in principle, the proof is again based on eigenfunction expansion and the asymptotic expansion. And quite lengthy, but already this was published in inverse problems or imaging. Okay, then maybe just for your reference, finally, please let me talk about the 2 pages, namely general treatment or general strategy for the uniqueness of inverse problems determining of initial value. How to prove? And already more or less I stated, namely we based like eigenfunction expansion and Laplace transform analyticity and some special property of the mid-Agrafla functions. Okay, then our formulation as the test case, we assume that arbitrarily chosen subdomain omega over 0 to capital T, let us assume this is 0. Then we want to prove that initial value is 0. Then we can prove that by the eigenfunction expansion ux for any fixed x. This is T-analytic. Therefore, we can extend this vanishing to infinity. Then we will take Laplace transform. Then also we apply a formula of the Laplace transform of fractional derivative u minus a. Sorry, this is totally taking Laplace transform. Then this is given by lambda alpha u Laplace transform minus lambda alpha minus 1 initial value. Then here more or less very similar. Then we will substitute this Laplace transformation formula. Then under the assumption minus lambda power alpha is in resolvent, we will take the inverse. Also, possibility of the Laplace transform, the other part of lambda alpha must be sufficiently large. Then plugged in our condition. Actually, this resolvent must be 0. Value of the resolvent of A must vanish in small omega if lambda alpha is not minus eigenvalue. Then after that, in this case, we will take Cauchy integral. Sorry, before that, we must apply holomorphic, so-called holomorphy or complex analyticity of the resolvent. Therefore, this can be extended holomorphically for all resolvent set minus lambda alpha. This means that z minus a inverse a equals 0 in small omega. If z is not in the spectrum or not in the set of eigenvalues. Then after that, this is a bit tricky, but rather common classical technique. Namely, we will take the sufficiently small circle centered lambda n eigenvalue, then taking Cauchy integral cycle, closed curve. Then resolvent and the Cauchy integral gives eigenprojection. Therefore, this means that for lambda n, eigenprojection of A is 0 in small omega, not yet in whole domain omega. Okay, but PNA is 0 in small omega, but PNA itself is nothing but eigenfunction or belonging to the eigenspace of lambda n. Therefore, after taking operation of A, this is just a scalar multiplication by lambda n. But PNA satisfies elliptic equation A minus lambda n. A minus lambda n PNA equals 0. Moreover, PNA is vanishing in small omega. Therefore, classical unique continuation, this means that if some function satisfies homogeneous elliptic equation and small omega vanishing, automatically that function must be 0 everywhere in capital omega. Therefore, we conclude that PNA is not only in small omega, but in capital omega 0. But n is arbitrary. Therefore, all eigen elements is vanishing in omega. Therefore, completeness or possibility inequality, once again, A must be 0. This is more or less a representative argument for proving initial value of some spatial unknown functions by means of extra data. Now, I think more or less the time is over. Then maybe according to the title, I would like to skip the part of the forward problem. But now I would like to, okay. Also, so far, we are concentrating on L2, namely in time direction L2 space, also in omega L2 space. And the existing works are mostly treating L2 omega. But naturally, not only L2, but LP omega space. That is also important, especially for treating nonlinear equations. Therefore, I am working for such LP theory, mainly the forward problem. Now, I would like to finish my talk. Thank you very much for your kind attention. Thank you very much.
Thank you very much, Professor Yamamoto, for the presentation. Do we have any questions, comments? Any remarks from the audience? You can unmute yourself or simply raise your hand. If not, then once again, I would like to thank the speaker for the presentation.
Thank you very much. Thank you very much. As I mentioned that, especially to the younger, I believe that there are many interesting topics to be done. Then I hope that, of course, I will not include the senior, but especially the younger are very welcome for starting. Also, I started more or less 10 years ago. Yeah.